brief case binder, but that's there for you to go ahead and kind of look over and ask questions definitely if you have them. Today, what we're going to be looking at is integrating with inverse trig. Do want to acknowledge that if you are new to me this semester, as in you came from Gav's first semester, you unfortunately did not learn how to take the derivative of inverse trig. So I'm going to do like an ever quick review for you, slash probably everyone else needs a good review of the derivative of inverse trig anyways. But then we're going to talk about how we can integrate with inverse trig. We'll do most of the day today will be notes. Like I'll go ahead and say heads up, I know it's a Friday, but we will do some lengthier notes today. Monday we'll finish the notes and look at some of the other examples with integrating with inverse trig. And then Tuesday is going to be basically a day like work and ask questions on integrating with inverse trig. And apparently I just left off Thursday completely of next week.
I was about to ask about
Yeah, I don't know where that went. But I have basically, after we finish like inverse trig, 3 days, I don't know again where Thursday went, but 3 days of basically reviewing for your test. Is a long weekend, but basically we'll be reviewing Wednesday, Thursday, and then Tuesday of the following week, and then testing on this unit on the 17th. Again, my hope is that you feel like you can integrate anything that's thrown at you by the day of that test, just because everything else is going to be applications of integrals.
It's the 11th. Yeah.
It's the 11th, yes, because we're definitely going from the 10-10, because I'm a math teacher and I can count up by 1. There we go. And now it's a different color. Oh, so that's kind of how like the rest of this unit is going to work. So let's review derivatives of inverse trig first. Good review for those of you who had me, and then just kind of need to know this if you didn't have me. But when we take the derivative of inverse trig functions, there are 6 of them, but it's really easy to just memorize 3 of them because all the co-ones are just going to be the negative version of the one they're related to. So like if we do arc cosine, arc cotangent, arc cosecant, all of those, if you remember, are negative. And when I say inverse trig, you might have more likely written it in pre-calculus, depending on who your teacher was, as like inverse tangent or whatnot, with like that -1 as like the inverse symbol. In calculus, we tend to avoid that notation just because we rewrite things with negative exponents so often. We don't want to confuse inverses with like an inverse function. So we will typically use like the arc version of it. So same thing, but just kind of a little bit less confusing, I think, with negative exponents. And then the rules that we have, I'm just going to kind of write them up here quickly, and then I'll tell you just about them. I use U here just to remind you that the chain rule does have to apply. Tangent to me is the easy one. The formula is 1 over 1 plus the inside squared. I'm putting a U prime here just to remember that we always need to do the chain rule when we're doing the derivative. Our cotangent is literally the same rule, but instead of a positive, it's going to be the negative of it. And again, chain rule. Arc sine and arc cosine are related. They have a square root sign in them and a minus sign. And that is a 1. Arc cosine is just the negative version of arc sine. And then arc secant and arc cosecant are the weird ones. They have square roots in them and absolute values in them. The derivative of arc secant looks like this: 1 over the absolute value of u times the square root of u squared minus 1, chain rule. While arc cosecant is the exact same thing, but negative. So again, any of your co-functions will be minus. Differences between them, I kind of think about how arctangent and arccotangent does not have a square root, and it has plus signs. Arcsine will always be subtracting the variable inside of a square root sign, while arcsecant will have like the weird absolute value in it, and also inside the radical sign, the variable will come before the subtraction sign in the formula. I'm going to do at least one example of just taking the derivative, just to remind everyone what it looks like when we take the derivative. And then we'll just talk about integrating. Because honestly, like I know some of you have not learned how to take the derivative, but this unit we really are just going to focus on integrating. You don't have to take the derivative to integral because it's just going to be like its own rule to memorize. But I do think it's nice to kind of see an example of a derivative worked out, kind of make the connection between the integral and the derivative. What makes these, I think, a little bit more challenging to do is definitely, just squeeze up there. Definitely, there's usually a lot of algebra involved when you're simplifying your answer. If you remember that from first semester and you had me. If I were to make up an example, let's just do arctangent. That's like the easiest one, but it will let you see what I want you to see. So if I tell you to take the arctangent of, we'll say, x over 5, we're going to go ahead and use that arctangent rule. The arctangent rule, again, is 1 over 1 plus the inside squared, and then, of course, multiply by the derivative of the inside, which is the chain rule. So taking the derivative of this, we have 1 over 1 plus the inside squared. So I have that x over 5 squared times, now for the chain rule, the derivative of the inside. Don't make it harder than it needs to be. X over 5 is just the same thing as 1/5 of x. So the derivative of x over 5 is just 1/5. I am going to simplify this because what's written in blue right now, you'll never have like the integral of what's in blue. Like it's going to be rewritten and simplified. How we often simplify inverse trig, so I'm just going to take that 1/5 and move it out in front. It really is just a coefficient. I just kind of want to ignore it for right now. Simplifying the main fraction part, I have 1 plus x over 5 squared. Well, what is x over 5 squared? It is just x squared over 25. One kind of gross thing that happens when you do the derivative of inverse trig functions is you often end up with like denominators within denominators, or just like a lot of simplifying and a lot of algebra to take care of. Right now, if I'm simplifying this one, that extra 25 is like a denominator within a denominator, just like in the way. It's not simplified. There's different routes you can do to simplify it, but I think the easiest way to simplify it is to multiply it by 1. Like we can't change the problem, so we're going to multiply it by 1. We're not going to multiply by any 1, we just want to multiply by 1 that will cancel out a 25. Well, what's going to cancel out the 25? Well, I can multiply by 25 over 25. Again, I'm not changing the problem, I'm just multiplying by 1, but it will let me simplify this fraction a little bit better. Multiplying fractions, you definitely multiply straight across, so you'll like have 1 times 25, distribute 1 times 25, and then x squared over 25 times the 25. Simplifying, I still have that 1/4 to deal with. Times 1 times 25 is 25. Distributing in the denominator, 1 times 25 is 25. X squared over 25 times 25, I'm saying 25 a lot, is just going to give you x squared. So we've kind of gotten rid of that extra denominator that was there. And then just to kind of get to the final answer, well, 5 goes into 25 5 times. And so we have a simplified answer of 5 over 25 plus x squared. And that is the derivative of the arctangent of x over 5. Many of you might remember, especially if you had me first semester, a lot of these questions I put on your quiz and your test, I would make you like first find the derivative, and then these are one of the few I made multiple choice, like match it to your answer, A, B, C, or D, because I wanted you to practice that simplifying. I show you all that, one, because we know that the derivative is basically the reverse of the integral. So what we're going to be focusing on today is basically what I have boxed in red. We say, let's take the integral of that, and we want to have a way to figure out how the integral of what's in red would give you that original problem that I have in black. So we're going to talk about how we would undo this. I will say, thankfully, I think the algebra usually is a few less steps when you're doing the integral as opposed to the derivative, only because we're going to memorize kind of like a new formula that has that algebra just built into it. So I will shorten some steps just by giving you like a straightforward rule. But that's basically what we're going to be looking at today. The last thing I'll say, and then we'll start with integration. With the derivative rules, there's 6 of them. So we had arctan, arcsine, arcsecant, and then the 3 arc cofunctions. When it comes to integrating, since the derivative only differed by like a positive and a negative, we're able to actually simplify this and only need to learn 3 integration rules, which is nice. So we can take 6 derivative rules and turn them into just 3 integration rules. So let's go ahead and start with integral rules. This will be the first type of integral that we're going to talk about. So I have the integral of 1 over 1 plus x squared. This is the most simple, most basic type of inverse trig problem that I could come up with. And this one's going to come straight from the derivative rule. Well, which inverse trig is going to be the integral of 1 over 1 plus x squared? Our tangent is the one that it looks like. That's coming straight from the derivative rule. And so this is basically the reverse of the derivative rule. I have the or here because technically, mathematically, yes, you can say the integral of 1 over 1 plus x squared is arctangent of x plus c. It's also equal to the negative arc cotangent of x plus c. For us, we're always going to use arctangent, not the negative arc cotangent. On the AP exam, they will always use arctangent and not the negative arc cotangent. I only kind of give that to you as like extra information, and maybe if you take calculus in college, the professor will kind of use both of them, but we're only going to use the arctangent one. Let's talk about how we know this is inverse trig. So I teach it in this unit because we've been integrating a whole lot of quotients. Like we have rewrite with the negative exponent, we have like long division, we have natural log problems. What makes this one an inverse trig problem and not a natural log problem? The short answer is basically the u sub doesn't work if you tried to make it a natural log problem. Like it's raised to the first power. So if this would be a natural log problem, you'd be like, okay, let u be the entire denominator. So u prime would just be 2x. Well, looking at that 2x, my numerator just has a 1 in it. So we're not going to be able to do our normal u substitution. It's not going to be a natural log. The longer answer to this and how I can tell easily that this is an inverse trig and not a natural log is I'm going to compare the degree of the numerator to the degree of the denominator. If the degree of the denominator is more than 1, larger than the numerators, then we know that this is going to be an inverse trig problem. So for example, I knew this one was not a natural log problem and it was an inverse trig problem. The largest exponent I see in my denominator is 2. And then technically, what's the largest exponent we see in the numerator? 0, because technically there's no variable there. Why is it not there? Because it's technically an x to the 0th power. 2 is more than 1 bigger than 0. So that's our big clue that's going to be an inverse trig problem. Now I told you that that's the most basic case where we have a bunch of 1s and an x squared. You know, honestly, nothing in calculus is always going to be the most basic case. We're never going to have just a bunch of 1s there. So this is going to be the general formula that if you memorize anything today, it's going to be like the general ones. And the general formula is basically, we're going to be looking for this constant a squared. So a is going to represent some number. It comes from the derivative rule, like when you're simplifying, but we really are going to need to identify, like, there'll be some number there. Maybe it's like 25 plus x squared. So then our a value would be 5. And the formula that I want us to memorize is going to be, when we see that integral, its antiderivative will be 1 over a arctangent of x over a plus c. So there is your first of 3 new integral rules for today. And then an easy basic example. Looking at that example, let's talk about why we know it's an inverse trig one. So like, yes, the denominator is raised to the first power, but it couldn't be a natural log problem because the u sub wouldn't work. How do I know u sub wouldn't work? The degree of the denominator is 2, and the degree of the numerator is 0. The denominator is more than one larger than what's in the numerator, so it has to be inverse trig. And this format is the arctangent one. So we are going to have 3 inverse trig rules. Arctangent is going to be the easiest one to identify because you'll have a plus sign and no square root sign. So it will be, and to me, usually the most obvious one. This is a 25 in front. Well, what squared is going to give you 25? 5. So I know that a value is going to be 5. So then the integral of this, we're just going to go straight to the rule. It's 1 over a, which is 5, arctangent of x over a, which is again 5, and then of course don't forget your plus c. And that's it. So there's not going to be like any rewriting. We just have to kind of recognize it, that it looks like an inverse trig, match it up to which inverse trig formula it is, and then integrate it from there. So that's arctangent. The second one that I want to look at before we do a bunch of examples would be ones that have a square root sign in them. So we do have 2 inverse trig rules that are going to have square root signs in them. The one that's going to be more common is when you have the variable after the subtraction sign. When you have the variable after the subtraction sign and square root sign, that's going to be the arc sign rule for integration. So in the most basic form, you'll just see a bunch of 1s, and if you see the square root of 1 minus x squared, we just 1 in the numerator, then we know the antiderivative is the arc sign of x plus c. That's the most basic case. That's the one I want us to know. Technically, it's also equal to the negative arc cosine of x plus c, but we don't need to really know that one for AB or BC. We don't really need to know for AP Calc. That's just kind of like extra information. Of course, we're not always going to have that most basic case. There often will be a number other than 1 that you're subtracting the x squared from. The formula in the general case, and be careful when you write this down, it's just the arc sign of x over a plus c. Do want to make sure you notice there is no 1 over a in front, so don't accidentally memorize the rule incorrectly for arc sign. I'm going to switch back to arctangent, and I'll come right back to this slide. For arctangent, it does have a 1 over a in front, so you do want to make sure you kind of keep that separated in your head as you're memorizing it. The short answer for why there is no 1 over a, it kind of deals with like the square root sign, and if you did all the algebra, it would cancel out. But for us, it's just going to be easier to memorize. Arc sign does not have a 1 over a built into it in front. So then the most basic example I could come up with, use that same 25, but I rewrote it so it looks like an arc sine rule. I know it's arc sine because of the differences between the degrees in the numerator and the denominator. The denominator is winning it out by more than 1. The variable is being subtracted, so I know it's going to be the arc sine rule. And again, our a value is going to be 5 because 5 squared is going to give you 25. So using the rule, this is arc sine, so it does not have 1 over a. So we're just going to go ahead and jump into arc sine of x over a plus c. Questions on that rule? All right, and then we have our secant rule, and this will be the third rule that we're looking at. Secant's going to be kind of the weird one. So I have the integral of 1 over x times the square root of x squared minus 1. Clues that this is a secant one. Clearly there's a square root there. For the secant one, the variable will come before the subtraction sign. You'll also have to have on the outside of the radical, like what is being squared. So if I have x squared on the inside, then I need to have an x on the outside. If you remember for the derivative rule, in the derivative rule, there's absolute value signs around that x. In the integral, they kind of show up on the other side. They kind of show up in the answer. So we're going to memorize that the integral of this, written in this format, is going to be the arc secant of the absolute value of x plus c. Or, technically, mathematically, it's the arc cosecant of the absolute value of x plus c. But we're honestly not going to use that in this class. We're going to use arc secant instead. Of course, like all the other ones, that 1 is often not a 1. We will have a number there that we need to identify, still using that a value instead. Arcsecant is going to be like the arctangent one, so it will have a 1 over a in front. And then we have the arcsecant on the absolute value of x over a plus c. And there is your third of 3 rules and final integral rule you'll need to know for this class. And I just have one easy example, and then we'll start kind of looking at some other ones. Try that for me. And again, it's pretty straightforward, but let's kind of talk about how we know it's arcsecant. So I first know that it's inverse trig because the degree in the numerator is 0, the degree in the denominator is 2. The denominator is more than 1 larger than the numerator. I know it has to be arcsecant because the x is coming before the subtraction sign, and we have something stuck on the outside of it. I keep using this 25 just to be consistent for the notes, but we can see that a would be equal to 5. So what would be the integral of this one? 1 over 5 arcsecant on the absolute value of x over a, which is also 5 plus c. Those absolute value signs are necessary and important. Yes, Mitch?
What if we don't get a perfect square like 25?
Good question. So if you were subtracting, say, 7, then your a value could just be like the square root of 7. So you can always make something squared.
Would that make the square root on the bottom? You'd have to like move the square root to the numerator?
You wouldn't have to rationalize. No.
Okay.
You can leave it in the denominator. So let's go ahead and summarize those rules. Like, I know it kind of seems redundant just to kind of go ahead and repeat this, but I think it's nice when you learn new rules just to kind of see them all side by side so you can kind of compare them. So you may not want to rewrite these, but I will kind of talk about them. I put both of these on here, so the ones that are dotted are coming straight from the derivative rules. So like if you've had me last year, hopefully you already remember those derivative rules, so like you can kind of do those automatically. If you're like, Mr. Brown, just tell me the bare minimum I need to memorize. Bare minimum you need to memorize what I'm going to put in the bolded boxes. Because technically, like this first one is the basic case, where we'd have 1 over 1 plus u squared. And I know that that would be arctangent. Technically, if you know that one, then you do know the other one. And if it's 1 there, then technically your a value is just 1. So like you can get away with just memorizing what you see on the right-hand side. I did put a u here because we often have to remind ourselves that u substitution is a thing that will always be around for us now. So we will often still have to do u substitution with inverse trig. The arcsine one is when we have the most basic rule. So this was the rule you learned when you did the derivative. Now with the integral, we kind of have this a value here. Arcsine is the weird one that doesn't have 1 over a in front. That doesn't mean it can't have coefficients. It can be do u sub, but it doesn't have a coefficient built in with the formula. And then the arcsecant one, here's the derivative of arcsecant that we learned. And again, the variable then minus the 1. Often we won't have a 1 there, so if you just want to memorize something, you're memorizing this row. An absolute value. So I put the u on these again because u substitution is going to be something that we have to look at. We'll look at problems today that have u substitution. And when you're doing u substitution with inverse trig, instead of setting like the entire denominator equal to u, or instead of setting what's inside the radical sign equal to u, you're just going to figure out what something squared is, and that's going to be the u value that you carry across. So we're going to look at several examples today. I'm going to start off with like the most basic ones. I will say I'm going to save arcsecant examples for Monday. We're just really going to focus on arcsine and arctangent, just to kind of focus on something. We'll start off again easy and then kind of build and look at examples that have u substitution, and then we'll finish up these notes on Monday. But today we're going to do mostly like straightforward kind of problems. And I know some of you are still writing this down, so I'll give you a little bit longer and then we'll go to the next slide. Questions so far? All right, let's look at some examples. So I did share this with you. I keep using my highlighter. I know I didn't really teach with this flowchart too much, but like I had made it previously, but I honestly think it makes things more confusing than they actually need to be. What I do want to focus on, and again, I know I didn't really teach with the flowchart, is really this very bottom part. I often find once I teach inverse trig rules, students sometimes have a hard time deciding, like, is this a natural log rule or is it an inverse trig rule? They do look very, very similar. And again, you want to just be able to compare the degrees that you see. If the denominator degree is more than one larger than the numerator, definitely, probably inverse trig. If the degree of the denominator is just one bigger, then it's going to be a natural log rule. And if all else fails, like just try the u sub and see if it's going to work. If the u sub doesn't work, then try the other rule. So let's go ahead and look at examples. Start off easy. Try that one for me. Probably could delete the heading and make us discuss why we know it's arctangent. Some people also get bothered when they see that dx up top. That dx is honestly the same thing if you wrote it out to the side. So don't overthink that part of it. So as you're working on this one, let's talk, how do I know this is inverse trig and not regular u sub? I know this is inverse trig because this is definitely the denominator's degree is more than one larger than what we see in the numerator. In fact, there's no variables in the numerator, and you have an x squared in the denominator. I know I said it was arctangent in the heading. How do I know this is arctangent? There's no square root signs, and there's a plus sign between what we see in the denominator. Do you want to identify the a value? This is a 16, so what is your a value going to be? 4. 4 squared is 16, and then we can just jump straight to the rule. Arctangent is 1 over a. Arctangent of x over a plus c. Easy, easy enough. I do want to make sure we compare this with ones that we've done. So for example, I'm going to kind of say just like what if. What if I just changed the problem slightly, left the denominator the same, but instead put an x in the numerator instead of a 1? What rule did I just make that in a rule now? U sub and then natural log rule. So just by changing that, and again, that's why I want to be careful. The difference of the degrees is just 1, not more than 1. So this one is actually a U sub problem. And it's going to become a natural log rule instead of an inverse trig rule. So you can kind of see just by changing the problem a little bit, I've completely changed the rule and how you would approach it. So we are going to have to make sure we look at our problems closely so that we don't mix up our rules. Try that one for me. Again, that's going to be a pretty straightforward, easy one. And then we'll kick it up a tiny notch on the next slide. I'm going to keep talking. How do I know this is an inverse trig? The difference of degrees is more than 1. We have a squared on the bottom and no x's in the numerator. I know I called it arcsine on the slide. How do I know it's arcsine? The big giveaway is we're subtracting the variable. That's what's telling us it's going to be arcsine, in addition to, of course, the square root sign. What's the a value going to be for this one? 3. And then you do want to make sure you're careful with the rule. Arcsine is the only one that doesn't have 1 over a in front of it, so we're just going to jump into it. Arcsine of x over a plus c. Again, arcsine does not have 1 over a in front, so make sure you don't add it in front. Those are easy, and honestly, like you can see problems like that that are that easy. Where they kind of change a little bit will be something like this. And I'm going to actually work this one out 2 different ways. You get the same answer both ways, but I've honestly, from experience, have found that some students like it's almost equal, like which way students prefer how to do it. The first way is to do u substitution. That's kind of how I tend to do it. Like if I just automatically see the u sub, then I just kind of jump right into it. Let's look at it right now, though. What tells us that this is an inverse trig problem and not a natural log problem? The degree. So we have no variables in the numerator, but an x squared in the denominator. So we know it has to be inverse trig. I'm not going to ask this question because it's so obvious, I think, but we know it's arctangent because we have no square root sign and a plus sign between them. So the arctangent rule, in order to help us figure out what the u needs to be, arctangent in its most basic format is like a squared or 1 plus u squared. So I want to think of this as an arctangent problem. So I basically need to figure out like what squared is going to give you the 4x squared. Well, easy enough. What squared is going to give you the 4x squared? 2x. And that is what your u is going to be. And that, I think, is what makes inverse trig so much different from a regular natural log problem. In a regular natural log problem, you're used to letting the entire denominator be your u. For inverse trig, it's just what's being squared that's going to be your u. So I would have u is equal to 2x. U prime would be equal to 2. Many of you could skip this step. I'm going to write it out. We have 1 plus u squared. Dx is du over u prime. And now I can go ahead and integrate it. Now that is clearly the arctangent rule. I have an over 2 out in front, which is going to give me 1/2. 1 over a, but our a value is just 1 because of the 1 there. So I'm going to go ahead and have the arctangent of u over a. Again, a is 1, so it's just 2x, and that is your answer. If you're good with u substitution, then like that will be your method to use. Like learn it, love it, use it. Another way to do that problem, you're going to get the same answer. Some students prefer this way. It's not my go-to, but honestly, I do see enough that I want to show it to you. And the other way to do this problem is just be like, I don't want to do u sub, so let me just rewrite it so I don't have to do u sub. And what do I mean by rewriting it so we don't have to do u sub? Well, if I didn't want to have to do u sub, what number in the original problem is really forcing me to do the u sub? The 4, right? That 4 is making me have to do the u sub. Well, if I can just get rid of it, then I can avoid doing u sub. We can't just like make it disappear, but we can manipulate it algebraically. And to do that, we can just like factor it out from the x squared. Like mathematically, we factor out the 4. But if I factor out that 4, what is that 1 going to turn into? 1/4. 1/4 times 4 is 1. Don't need to do u sub, but now we do have an a value. What squared is going to give you 1/4? 1/2, right? 1/2 squared is 1/4. No u sub because that is just x squared. So when I go to integrate it, so I have this 4 in the denominator that I can't forget about. That would just be a 1/4. There is an a value now. This is arctangent. So I would have times 1 over a. Arctangent of no u sub, so x over a plus c. Most of you wouldn't write it that way because of those extra denominators in the denominators, but we know that dividing by a fraction is just the reciprocal. So like 1 divided by 1/2 is just the same thing as 2. Well, 1/4 times 2 is just going to give you what? 1/2, which again is what we expected. And then we have the arctangent. X divided by 1/2 is really just the same thing as saying 2x, right? 2 times x plus c. You get the exact same answer. So again, I don't care how you do it. Pick a method and like learn it and know how to use it. Questions on that one? Try this one for me on your own. Again, that dx you can kind of move off to the side. I am going to work this one out two different ways. Again, I think U sub personally is my favorite way, but again, other people see it other ways as well. Not going to finish it. I'm just going to kind of do the first step of it, and then we'll kind of regroup and talk about both methods. Yes.
With this one, it matters like which order you put it in, right? Because it's like there's subtraction at the beginning.
I guess when you say order matters, like I'm subtracting the variable, and that's my clue. That's going to be an arcsine problem and not an arcsecant problem. So that's kind of what you're recognizing that matters. So two ways to do this one. The U sub way I'm going to do first, just because that's kind of my preference personally. We know this is arcsine. How do I know it's arcsine? The denominator's degree is bigger by more than 1 when compared to the numerator. If it is arcsine, let me not make that a plus sign, but a minus sign. Make sure you fix that if you're copying down exactly what you saw. We want to think of that as something squared. Well, 25x squared is the same thing as 5x squared. So u would, of course, be 5x, and u prime would just be 5. So we're really just integrating 1 over the square root of 1 minus u squared. Dx is du over u prime. So integrating this one, I know this is arcsine, and arcsine does not have a 1 over a in front, but we still have u sub, which is going to give it a coefficient. So I have 1 over 5 arcsine of u, which was 5x. A value is technically 1, so not going to worry about it, plus c. Method 1, yes, Marcus?
So you have like a 7x squared, right? There would be like use your whatever u is like square root of 7x.
Yes.
Yeah.
Mm-hmm. So that's the first method. The other method is, again, just kind of force out the u sub. Well, how do you force out the u sub? You're like, man, I really wish this 25 was not there. How do you make it not there? You factor it out. So when I factor it out, that's going to turn into 1 over 25 minus x squared. Do be careful here. When you factor it out, it's still going to be stuck underneath a square root sign. So then when I go to answer it, this is 1 over the square root of 25, which is 1/5. My a value, what squared is 1 over 25? 1/5. No u sub when I rewrite it this way. This is arcsine, so there is no 1 over a in front. So I'm going to go ahead and jump into the arcsine of x over a plus c. X divided by 1/5 is the same thing as saying 5x. So you get to the same answer. I don't care how you do it, as long as you can do it correctly. Questions on that problem? All right, so that's where I'm going to stop at today because I don't really want to rush too much else. I do want to show you what we have to do just in case you are going to go ahead and start homework 3 this weekend. Just know that we haven't really done everything quite yet. So I was going to do another arcsecant example, particularly an arcsecant example that used some u substitution and also when we had a number that wasn't a perfect square. Then we're going to look at examples where the degree just differed by a lot, which is just going to be more u sub and inverse trig. Some weird examples. Everyone loves a weird example. And then everyone's absolute favorite, how we can use completing the square to do inverse trig. Promise you completing the square is not as difficult as your Algebra 2 teacher made it out to be. Also, you've grown mathematically, so it really is not going to be stressful. Like, you just add numbers and it works out nicely. But that's what we're going to look at on Monday. Again, looking at the calendar, like next week is a lot of just like reviewing and practicing. So there's going to be plenty of time to get the homework done, plenty of time to get like quiz corrections done, the briefcase binder and all of that. Assignment wise, if you are looking to work on some stuff this weekend, things that you can be working on. Homework 3, again, I'm not expecting you to do all of it. So I haven't finished this topic, but you can definitely start. Don't want you to forget about homework 0, those like kind of AP review questions you have this unit. And then just other general reminders. Unit 5, test corrections of recovery. I know many people have reached out to me, either turning in their corrections or letting me know they are taking a recovery test on Wednesday during office hours. You can also now, if you're just feeling extra eager, go ahead and start your Unit 6 quiz corrections as well. The key to the Unit 6 quiz is in that answer key folder. Other than that, I hope everyone has a good weekend. If you are at home,